feel so bad on this stuff that the video's not much or good for much other than the audio. So something I got to backtrack on just a little bit. We did all of the work with talking about rates, the rate of an individual step in a mechanism and relating it to activation energy, temperature. What else do we relate it to? Activation energy, temperature, and then the kind of orientational collisional parameters, the geometric constraints on reactivity, how only certain kinds of collision are actually sufficient for reaction. Those arguments that we made all apply to a single step in a mechanism. So if you can pick apart a mechanism and figure out all of the different individual steps that are required to get from point A to point B, then those arguments apply for one of those steps. An individual step where two reactant, or maybe not two, but where reactant molecules have to cross an energetic boundary and get to product molecules. The thing about reactions in general is that you can't necessarily just look at the reactants and the products of a reaction and make the assumption that the exact reactants are going to come together in one step and make products. It might be that your reactants move slowly through several different steps, or incrementally, through several different steps before they get to products. In that case, it's not safe to assume that your rate is going to have some K times the actual reactants that you see in the balanced equation. Your rate will be a function of the concentrations of your reactants, but here's how this works. If an individual reaction proceeds through many steps or several steps before it gets to final products, whichever one of those steps is the slowest step is going to be the step that determines the absolute rate of the mechanism, right? It's the bottleneck effect. Whatever step is slowest, nothing can proceed faster than that step. And so we're going to need to use this in about a half an hour when we start looking at practice exam problems. That said, you can cast the rate of a reaction in a forward direction in terms of the reactants and products. We're going to say, or reactants in this case, we're going to say that the rate is equal to some K, and we don't know exactly which K this is yet because we haven't identified the rate determining step. Let's say that we've got two reactants, A and B, times the concentrations of the reactants raised to some coefficient that we do not know yet. So we're not exactly sure how many A molecules, if any, are actually involved in the rate determining step. So we're going to put this generic coefficient up there. If we find out that there's one A molecule in the rate determining step, then that coefficient is going to be 1. If we find out that there's two A molecules in the rate determining step, that coefficient is going to be 2, etc. If it's also possible that there are absolutely 0 A molecules in the rate determining step. Maybe A is not involved in the rate determining step. Maybe B has to do something first before A can react. In that case, we make that coefficient 0. Anything with the 0 power is 1. And so basically what that says is A molecule is not involved in the rate determining step. And so once we get to practice exam problems, we're gonna get a chance to use that. I just wanted to point out to you that that is a thing, and you can't look at the mechanism and derive quickly a rate. You have to figure out which one is the rate determining step first, and then you get a rate. Okay, so we set up all this rate stuff. We talked about equilibrium. Equilibrium is when the rate forward is equal to the rate reverse. So when you have a reaction where the products kind of stay in that volume or space with the reactants, and the products can actually back react with each other to go on and form the reactants. If this is the case, then over time, as products build up, the rate of the back reaction will start to compare to the rate of the forward reaction. And eventually you'll get to a point where the two rates are equal, and at this point, the back reaction and the forward reaction still proceed, but there's no net change in the species inside the container. And this is equilibrium. Rate of the forward reaction is equal to the rate of the reverse reaction. Now, there's a couple special cases of equilibrium that we have not mentioned yet. We're gonna do those now. But before I get into those, there's one thing that I want to explain that I did not explain very well or fully in the beginning or in previous courses or lectures. When we looked at ionic solubility, and we were talking about the forces that are relevant to ionic solubility, I told you that we've got a competition for the ion-ion forces in the solid, right? Two ions get together in the solid, a positive and a negative, and they've got that potential lowering effect when the positive charge and negative charge comes together, right? So that favors the solid phase. We've got the ion dipole forces in the between the ion and the solvent water. That's an electrical potential lowering kind of a force when the water dipoles line up with the ionic charges. We have the entropy likes things to disperse. Matter likes to spread out. And so entropy actually favors the dissolved phase of those species. It's one other thing that I didn't really, I touched on it, I said something, but I didn't give it due justice. There are other forces in solution that are relevant to ionic solubility and the solubility of any charged species. We said that when ions dissolve in solution, they get solved by water. So you guys get my nomenclature there with the V's, those are the water dipoles surrounding the ions. Well, you get the electrical potential lowering from the solvation of the ions by the water dipoles. But another thing that happens is that these ions are sitting in the solution. They're separated from each other by possibly thousands of water molecules. But you still have a situation where you have positive charges and negative charges. And anytime positive charges and negative charges can get closer together, electrical potentials are lower. This creates a tendency for solvents that are polar and can facilitate, the kind of dipole forces that we are looking at here. It gives a tendency for these kinds of substances to like to have dissolved ions. If you have ions dissolved in solution, those ions can get together and have favorable electromagnetic forces between each other. It turns out that there's kind of the strength of those forces gets stronger as the concentrations of the ions in solution get larger. So if you only got two ions in solution, and one's over at this side of the container, and one's way over at that kind of side of the container, you don't have much electronic interaction. But when you've got a bunch of ions dissolved in that container, now you have that positive charge and negative charge are moving closer together, and there's more of those kinds of interactions. There's more of those interactions, the strength of those interactions are stronger, etc. It actually becomes easier to stick ions into solution as you're building up from zero concentration. At some point, though, that effect kind of, it doesn't die out, it still exists, but it gives way to another effect. And that effect is that every time you stick an ion in solution, you got to take a water molecule that was previously hydrogen bonded with other water molecules, and you got to orient it around that dipole. That's a lot of order, so it's kind of a low entropy state for the waters to order around those ionic, or the ions like that. And also it interrupts on some level hydrogen bonding. So when the water molecules are sitting around the ions like that, they lose on some level the ability to hydrogen bond with other water molecules. And so what happens is that eventually you get so many ions in solution that ions don't want to go in solution anymore. It's no longer energetically favorable. So at low ionic concentrations, the solution wants more ions. At medium ionic concentrations, it wants even more ions. It really wants to grab those ions and pull them in. But at high ionic concentrations, you lose the effect altogether, and you get to a point where the solution does not want to take on any more ions. All right? Now that is going to bring us into the question or the mathematical form of ionic solubility equations. Oh boy. Sorry. Hopefully you'll be able to read this on the photocopy or the scanned version of the notes. You have an ion that goes into solution. You've got two different phases. You've got the solid phase of the ion, and you've got the solid phase of the ion. Once you get to that point where you've reached the limits of solubility, you can't fit any more ions into the solution. Once you get there, you get to a place of equilibrium. You still have ions in the solid that are breaking apart and going in the liquid, but at the same rate, ions in the liquid are capturing each other and forming a solid. And so these ionic systems have an equilibria that they reach. For equilibria, we say that rate forward is equal to the rate reverse. For the forward reaction, we're going to have some K forward that describes the rate at which the ions are kind of breaking apart from the solid. The reactant in that is your solid. So we might be tempted to put a concentration of solid right here. Set that equal to the reverse reaction, which is going to be equal to K reverse times the concentration of whatever the positive ion is, raised to its coefficient, times whatever the concentration of the negative ion is, raised to its coefficient. And so if we were to try to form a K value for this, take a KEQ, we would say that KEQ is the ratio of the reactants to the power of their coefficients. So again, we're going to have a positive ion to its coefficient, negative ion to its coefficient, over concentration of the reactants. So it's a solid here to figure out why that's okay to say. And that would be equal to little k forward over little k reverse. Big KEQ is equal to little k forward over little k reverse. It's equal to the ratio of the products to their coefficients over the reactants to their coefficients. Now here's the thing. Concentrations, easy to express for positive and negative ions. But a solid doesn't have a true molar concentration in solution. It's not dispersed. There's not a moles per volume that you can state for that. I'm not going to give a very good reason for why or an explanation for why, but trust me when I tell you that in place of writing concentration of solid, it turns out that it's mathematically acceptable to just put a 1 right here. And it turns out that that equation will give you correct information on the solubility of your ionic system. And so, when we're writing out KEQ for ionic solubility processes, we change its name. We call it KSP for solubility product. And it's going to simply be equal to the concentration of the positive ion, so whatever its coefficient is, times the concentration of the negative ion to the power of whatever its coefficient is. And you can see from the form of the equation that the larger the value of K is, the more soluble that ionic solid is going to be. Large KSP, high solubility for that salt. Small KSP, low solubility for that salt. Okay? There's your introduction to it. I'm not going to do any problems with it right now. We'll have a chance to do those when we practice for the exam. One other kind of equilibria that we need to discuss, a special kind of equilibria, is quote-unquote acid-base equilibria. So we said that solutions like to have dissolved ions, right? There's kind of an electrical potential lowering effect that happens when those ions dissolve inside the solution. And so as long as the forces in, for instance, the solid or whatever forces they are that hold the would-be oppositely charged species together, as long as those forces aren't too strong, then ions will tend to dissolve in solution on some level. Right? The solution likes to take on ions. It gives an electrical potential lowering effect. Well, turns out that many molecular compounds, so this solubility was about ionic compounds, but many molecular compounds have the ability to break apart in polar solvents and create charged species that disperse through the solution. Different ways that you can do this, but imagine you've got a neutrally charged species. You break it into two pieces. One's got an extra piece of positive charge, and one's got an extra piece of negative charge. Those things can dissolve in solution, become solvated by the water dipoles, lowering their potential. They have that effect on each other, where when the solvated ions get together, you have the lowering of the potentials. They like to do this. Molecules like to do this. There's a particular variation of this process that we're going to look at right now. And that is when these molecular speed or substances break apart by losing a proton. You kick off one proton, you just lost a positive charge. Now, whatever your base molecule was, that thing's negatively charged. The positive and the negative separate in the solution. They get solvated by water, and you get that electric potential lowering thing. So, I told you we like to have polar solvents for this, because polar solvents like to solvate charged species. In the case of, I think this is called Lewis, but it might be called Bronsted-Lowry. My vocabulary is horrible. In one particular variation of this, what's required is that the solvent, or in the variation where you lose the proton, what's required is that the solvent species has lone pair electrons. Protons like to land on lone pair electrons. Can you see this drawing very well back there? Can you see what that is? Okay, I'm going to redraw it then. So what I have here, I've written parent molecule plus water, and when I drew out the water, I made sure to include the lone pair electrons that exist on that water. And what happens is that the parent molecule has an H+, so I should just draw parent dash H. When that H sees that water molecule, it's going to pop off and land on the lone pair. What you're going to be left with is a parent molecule that has a negative charge, but it also has now a free lone pair right where the hydrogen previously had been. So we'll call this parent minus. And now you've got this water molecule that has 3 hydrogens sitting on it and 1 free lone pair. It's called the hydronium ion, H3O+. Well, you get enough of these H3O+s and negatively charged bodies of the parent molecule dispersed in solution, and eventually the back reaction is going to catch up with forward reaction, yeah? So you start off with these guys, you start making a bunch of these guys, but as these build up, the back reaction catches up with the rate of the forward reaction, you got a new equilibrium. real quick, I'm going to switch my, my nomenclature. This parent molecule, I'm going to call it HA. This guy, H2O, going on to form A minus plus H3O. Well, if that's an equilibrium, then we can write it out as a equality of the rates. So K forward times conc HA to the 1, in this case, we have 1 HA molecule, times conc H2O to the 1, in this case, because we only have 1 H2O molecule, is equal to K reverse conc A minus to the 1 times conc H3O plus to the 1. Putting all the concentration terms on one side and the K's on the other to get a KEQ, we have that KEQ is equal to conc A minus to the first, conc H3O to the first over conc HA to the first times conc H2O first, right? So this should be our equilibrium constant K. We're going to throw one little curveball at you with this. In this reaction, one of the particles that interacted, one of the species that interacted was the solvent. So if this happened in water, water's the solvent, you saw that water was necessary, the lone pairs on water were necessary to facilitate removal of the proton from the parent molecule. And so the solvent actually shows up in the equilibrium expression. Well, this gives, this facilitates writing of the equilibrium expression in a simpler form. In truth, most of these solutions that we're doing these reactions in are dilute. And so because they're dilute solutions, the concentration of the solvent, in this case water, is relatively constant throughout the reaction. Even if a few water molecules go on to, accept protons and become H3O plus, not many did. The bulk of them stayed in exactly the form they were at. And so in these systems, conc H2O is approximately constant. Well, because that's constant, we're going to take this guy out of the denominator of the right-hand side of the equation, and we're just going to stick it over here into the numerator of the left-hand side of the equation and let it be absorbed into our other constant here that we had KEQ. So we'll give the equilibrium constant a new name now. We'll call it Ka. And we'll say Ka is equal to KEQ times conc H2O to whatever its coefficient is. And that's going to be equal to concentration of A minus to its coefficient, concentration, of H3O plus its coefficient over concentration of HA. So all we've really done there is to rewrite a special version of the equilibrium constant that absorbs the approximately constant concentration of the solvent, which is acting in that equilibrium. All right? So you'll see for normal reactions, you'll see the full equilibrium expression, products to the powers of their coefficients over reactants to the powers of their coefficients. If you're dealing with ionic equilibria, you'll see something like this, where it appears that only the products are being accounted for because the reactants are solids and they don't actually end up showing up in the equilibrium expression. And if you're dealing with a quote-unquote acid-base equilibria, where solvent is picking off these protons, then your equilibrium is going to be given by the Ka, the acidity equilibrium constant, and you'll have conjugate acid, conjugate base over concentration of acid molecule. Okay? All right. So we're going to stop with those explanations for a second. We're just going to take a quick look at the practice exam. You guys need to be able to draw Lewis structures. You need to be able to draw Lewis structures, and you need to be able to evaluate them for which structures are the best. Problem 2 here, in the practice example, problem 1 asks you to compare several different Lewis structures of the molecule M2O by using formal charge. I encourage you to do that one. We're going to do H right now from problem 2, COCl2. Okay. Okay. COCl2. How many valence electrons do we have with COCl2? Cl, 7 valence electrons. We have 2 of them, so that's 14 valence electrons contributed by the 2 Cls. 14. Carbon's got 4, that brings us up to 18. Oxygen's got 6, that takes us to 24. So for COCl2, we have 24 electrons we need to account for. Carbon is the least electronegative of the species, and so all of the other species are going to go after carbon first when they try to fill their valence shells. So we'll stick carbon in the center, right? We'll stick an oxygen over here somewhere, and we'll stick some Cls over here. Draw our bonds, our first single bonds between the central molecules and peripheral, or central atom and peripheral atom. That cost us 6 electrons. So now we've got 18 electrons left that we got to get rid of. Start giving lone pairs to the peripheral atoms. Each of those guys needs 6 electrons in order to fill its valence shell. We just got rid of those 18 electrons. Those are gone. We have 0 electrons left to distribute. Now here's a problem. Carbon does not have its valence shell filled. And one of the most important things with these Lewis structures is to try to find a structure where all of the atoms, or as many atoms as possible, have filled valence shells. So we know that what we can do is take lone pairs from the surrounding atoms and draw them as bonding pairs. 3 different structures we can derive from this. We can move these 2 electrons from the Cl over to a bonding pair, or we can take electrons from the other Cl over to a bonding pair. The 2 structures that we get that way are going to be equivalent. Or we can take the lone pair electrons from the oxygen and make them bonding pairs. Well, let's try a couple of these. One variant over here. We'll do the oxygen. We'll move one of its lone pairs in the position of bonding pairs. We'll leave those Cls just as they are. In another variation over here, we'll leave the oxygen as it is. And we'll take a lone pair from one of the chlorines and move it into a bonding pair position. Which structure is best? Bueller. How do we know which structure is best? What do we got to do to evaluate the quality of the structure? Formal charge calculation. So what's the formal charge on that oxygen in the left-hand structure? Oxygen normally comes with 6 valence electrons. In our structure over here, it's got 2 lone pairs. So it's got 4 electrons in the form of those lone pairs. Plus, for the purpose of counting formal charges, we give them half of all the bonding pairs. This oxygen's got 2 bonds to carbon, so that's 4 bonding electrons. We give half of them to the oxygen, so that's 2. 2 plus 4 is 6. In our Lewis structure here, it shows the oxygen associated with 6 electrons. It comes with 6. It's associated with 6 in the structure. With 0 formal charge. Okay? Chlorines. Chlorines normally come with 7 electrons. Each of these chlorines has 6 electrons in the form of lone pairs. Plus, they've got